So thank you for coming back for the second set of lectures, and we'll continue to discuss harmonic functions with bounded frequency, meaning that we want to do something that can be generalized to solutions of elliptic PDEs. But today I will talk about mostly critical sets of harmonic functions and show you two ways to estimate the size of the critical set in dimension 2. One of them is very two-dimensional. The second one is, very analytic, very two-dimensional. But then we'll start third one that I'll also do in dimension 2, but that can be generalized to higher dimensions. But before we go to critical sets, let me remind you what we did last time. And I mentioned the following Ramus inequality for solutions of elliptic PDEs. Let me write harmonic. So we have a harmonic function with bounded frequency. We have a subset of a half-ball positive measure, and we claim that the maximum of the function over the unit ball is bounded by this construction constant, the ratio of the measures. Sorry, it should be 1/2 here. Constant times Cn plus 1, just in case, and maximum E here. Right, I want to write two equivalent formulations of this result. So one is the following. If you think a little bit what the frequency is, you can rewrite it in the following form. For some alpha between 0 and 1. So this is like our 3-ball theorem, but now the smallest ball is replaced by an arbitrary set of positive measure. And another equivalent formulation is that if we look at the set, say in half-ball, where the value of the function is small, then the measure of this set is small. It's a very simple algebraic exercise to check that all these three formulations are equivalent. Yes? No, that's not a question. Okay, and what we prove is actually this one. And this one we prove by induction on scales, looking at local version of this inequality and dividing a cube of ball into smaller ones, and using this idea that there is one piece where the frequency is less than this maximum one, less by quantitative constant, say 1/2 of the capital N, not the capital N. There is an improvement of this result that is in our joint work with Sasha Lagunov, both the initial one and the improvement as well. And it tells you that you can do extension or propagation of smallness not only from sets of positive measure, but basically sets of codimension larger than 1. We know that our function vanishes on a set that is codimension 1. So as soon as this is some set that has codimension larger than 1, we can hope to have an equality like that. And for that, the nice way to measure the size is not the Hausdorff measure, but Hausdorff content. That is the infimum sum of the radii to the power s, where our set is covered by those. So as soon as s is larger than n minus 1, and you have a quantitative estimate on this size of the set, you can have the corresponding result. For this, you need to know a bit more about the frequency, and not only that there is one place where the frequency is much smaller, but there are few places where the frequency is the largest one. And we always think about distribution of frequency by thinking about our harmonic function of solution to elliptic PDE in a cube, dividing this cube into smaller ones and looking at the cubes, trying to measure the frequency in the cubes. I go from balls to the cubes because cube is easier to tile the space with. And one lemma, due to log of that I mentioned last time, we already know that if there are 3 in the plane, or d plus 1 in dimension d, places where the frequency is close to maximum, then in the centrum it is even larger. So the distribution of pieces with the maximal frequency is specific. It can be some vertices of a simplex. If you think, what does it mean? It means that your largest frequencies should be concentrated along a hyperplane. And then there is another result that I will probably formulate later today that tells you that there are not too much largest frequency cubes on hyperplane as well. But let us postpone it for a while and go to nice, simple world of holomorphic functions. So as I said, this part will consist of 3 stories. The first one is simple and very specific for dimension 2 and very analytic. And this is an argument that is basically due to Han. And we will estimate the number of critical points of a harmonic function. By critical points, I always mean points where the gradient is 0. And for this, it's a bit better to change the definition of the frequency, because constant functions play no role here. So if we subtract a constant, nothing changes, and the frequency depends on this constant a lot. We don't like that, so let us define the upper frequency as the frequency of the function u minus the value of u at x0. Definitely this is larger than or equal to the frequency itself. Follows just from our example from our decomposition into spherical harmonics. Okay, so the statement is that the number of critical points saying half the ball is bounded by constant times the frequency, the upper frequency. Now the upper frequency now is never too small. When R goes to 0, the limit is positive. So I don't need to add 1 here. The main term is not vanishing there. Good. And as I said, our first proof is using complex analysis, and that means that I don't know how to extend it to elliptic PDEs for this proof. What we're going to use is Jensen's formula. Let me try to write it down in the correct way. So I have an analytic function, holomorphic function, in a disk of radius r. Then I can write the log of the value at 0 as sum of the logs of the zeros of this function over the r. So a k are all in the disk, and those are points where our function is 0. And then we have the average of log f. So if there is no zeros, log f is a harmonic function, and it's written that the value of 0 is the average over the boundary. If there are some zeros, Green's formula tells you that you should do this. I think this one we all remember, and I need another one. I want to change the 0 to another point, so I want to compose my function with a homomorphism of the disk. So take 1 point z0 in the disk and write this composition so that z0 is moved to 0 point by the inverse function. Then, if I do my algebra in the right way, we should get the following formula. Still over zeros of f, but now it's logs here. Yeah, something is wrong with my map. So I want phi of 0 to be this one. Okay, hopefully this is good. And then I have something there. You can write it more explicitly using the Poisson kernel, but it doesn't matter for us. So anyway, you can express the value of your function at any point using the zero set, 0 points in this disk, all of them, and the average of this log on the boundary. There was another way to clean the board yesterday. Yeah, thank you. So I'm going to bound the number of zeros in the disk of radius 1/10. You will see why I want something really small. And you can recover the result by covering this disk of 1/2 by smaller disks, such that 10 times those are still on the unit disk. So let A1 AK be the zeros of, yeah, I'm going a bit ahead of myself, I'm sorry for that. I need to have a harmonic function first, right? Sorry, a holomorphic function first. I have my harmonic function U, and I'm looking at the gradient. I will put the gradient, the complex valued function, and I claim that this is holomorphic. If you write U and this series, then F is a holomorphic function hopefully my sign is correct, of this form. And then it's easy to check that the frequency, upper frequency function U is larger than constant times frequency of F at any smaller radius, say 3/4. So now I want to estimate the number of zeros of an holomorphic function using the frequency of this holomorphic function. And it shouldn't be very difficult. So as I said, A1, AK now are zeros of F in a small disk, and say AK plus 1, AN are the zeros 2/3, D minus 1/10 there. And I'll take a point on the circle of radius 1/2 where my function takes the largest value. So Z0 is such that this is 1/2, and this is 0. And apply the Jensen's formula to this setup. My R will be 2/3, something between 1/2 and 3/4. So on the left-hand side, we have the log of f at this maximal point. Here we have terms that correspond to the zeros inside smaller disk. And then we have the other terms that we'll ignore. This is J. And finally, we have this term here. So those terms are negative. Each of those terms gives us some negative summand here, and we can bound these logs from above. They are all smaller than some negative quantity. So if I put this into the left-hand side, I will have a term that is the number of zeros times something positive, and on the right-hand side, I will have the difference between the average of my log at the circle of radius 2/3 minus the maximum at 1/2. This difference is bounded by the frequency. We know that the maximum is the same as L2 norm over a bit larger ball. So this is bounded by the maximum of the log of the absolute value of f. And if you look at the difference, you will find that k is bounded by constant. And also have like that. So it's a simple computation using Jensen's formula. And as I said, the disadvantage is that it's too analytic to think how you can do it for other equations, even in dimension 2. So the second story that is still very two-dimensional, I think, goes back to Donald and Pfefferman, who estimated the size of the zero sets of Laplace eigenfunctions on two-dimensional surfaces. And the tool is a very nice, very simple Korlemon inequality. It's one of the beautiful things in dimension 2 that you have very rich family of Korlemon inequalities. The Korlemon inequality is a weighted inequality between a norm over differential operator applied to a function and the function itself with some weight. So we will start with a function with compact support on a complex plane. It will be, sorry, just complex plane, complex valued. And my operator is just d bar. So what our weighted inequality, d bar of v with some weight, estimated by the integral of v with the same weight, and I want to know for which weights this can be done. And I think I remember the identity that I want to show, but it's so simple that I'll prove it. We take a function, now it's real valued, and assume that both are C2 functions, so that no problems doing integration by parts and partial derivatives. And we want to bound the or not bound, but first write the following integral. This is the integral of d bar u with a weight q. So I will do integration by parts. And introduce the following notation. It's very simple operator. It's d bar operator plus multiplication by d bar of phi. Right, so it's a sum of two operators, first order d bar and then zero order multiplication there. So we can rewrite it as minus u e phi d bar phi. Sorry, let me take away bar here, because I want it without bar, d bar. So I multiply by e minus phi, denoted it by e phi, and multiply by e to the power phi once again. And now we will interchange those two operators. The first term here, it's nice. Let us take e phi to this part and do integration by parts once again. Then you can see easily that this is d phi u, d phi u. It's a very nice positive term. The second one includes the commutator of those two operators. This is greater d plus multiplication by d phi. The first order parts commute. What is left, if you do it carefully, is just multiplication of function by d bar d phi. And we get nice identity. It's even not inequality, it's identity, that the integral for a complex plane, as I said, I was hoping to use notation v for my function, but it was not realistic. So I will use u, but it's not the same u as u in the first part of the lecture. This is not harmonic function, it's a function with compact support. And then our identity is that this is integral of d phi u squared e phi plus This is 1/4 of the Laplacian. And it tells you that as soon as your function is subharmonic, or better you control the Laplacian, know that it's large enough, you can estimate the L2 weighted with this e to the power phi of d bar by the integral of u squared with the same weight. So as soon as this is non-negative, say better than a constant, we can use this function for this operator. There are some other ways to write this identity and use part of this term using d phi with 2 instead of d phi here, and moving it into positive term and then having term with the gradient of u, but let me not go there. So the inequality that we will need is that if we have a function that is subharmonic on the support of u, then we have the inequality like that. And there are Kardemanian inequalities in higher dimensions as well. The problem there is that you should be much more careful with the weight. You can just use any subharmonic function. There are weights for which you can get Kardemanian inequalities, or the class is much smaller, and for each one it's a nice computation how to get there. But Kardemanian inequalities were there before frequency function to prove unique continuation results. It's a very nice machinery to prove unique continuation. One of the things that people usually do here, instead of looking at what inequality, you can introduce a parameter here. If I multiply my function by t, the Laplacian is multiplied by t, and they have a whole family of inequalities. I'll show how to use this kind of inequality to get another proof of our result. It's still a toy problem, but it's almost there, and you can do very similar other situations. Yeah, no, we said that if it's subharmonic, then we have this inequality. So for any subharmonic, if it's not subharmonic, we have still this identity, but we not always know how to use it. But there are situations where we can. So let me first say a couple of words what we should do to be honest. When d bar is a nice operator, but what I am going to show you that if you have a function for which d bar is bounded by a times f, then the number of zeros is still controlled. And as I said, it's still a toy problem. You can think about this and factorize this function into holomorphic and something not very bad. So more honest story would be to go for zeros of the gradients of harmonic functions or more honestly, solutions of, say, these inequalities and estimate the number of critical points here. This is more interesting bit than that one, but the technique is the same. I will do it on this level, but there are Riemann inequalities for the Laplace. And the simplest Riemann inequality you can get just from this one using the tau Laplace is d bar d. If you use this Riemann inequality for real valued functions twice, you will see, yeah, I'm missing a factor, right? It's 4 times this one. That so you have Riemann inequality for the Laplace in dimension 2 with any subharmonic weight. I'm just applying the inequality over there twice for real valued function. The gradient is twice du, and du and du is the same as d bar. There is another simple algebra with this identity. If you play a little bit more using the fact that u is real valued, you can have another Riemann inequality that is better because it includes a larger term in T. Yeah, probably I should write C squared here. If C is the estimate for our subharmonicity. So what I'm going to do for this equation, for this inequality, you can do for this one using the same arguments, but I'll have one more term to think about, and my computations will be a bit more technical, but the idea is still the same. So this proof works for all solutions to all equations that you can reduce to this, or even with the first order terms as well, but let us keep it for now. So how to use Riemann inequality for some kind of unique continuation result, because here it's unique continuation. We're saying our function is 0 up to order 2 at some points, and we want to know that it's 0 if this number of points is large compared to its frequency. Probably it's naive to hope that I'll do it before the break. Let me instead do 2 other things. There is a very nice argument using this Riemann inequality for d bar that is written in an article by Wolf, but he attributes it to Jerison, that solves or shows how you can use Riemann inequality to solve the following problem that is quite simple in dimension 2, but very difficult in higher dimensions. So Suppose that you have a function that is harmonic in a unit ball, and let me say very smooth up to the boundary. And we know that u is equal to 0, or that the gradient u is equal to 0, or u and its formal derivative is equal to 0. Let us say u is equal to 0, the gradient on a subset of the sphere of positive measure. In many references, this is called Beer's problem. So the surface measure of this set is positive. In dimension 2, this is true. And the gradient is an analytic function. You can use Privalov theorem to show that if you have an analytic function that is equal to 0 in a subset of the circle of positive measure, you don't need to know much about the regularity, then it's 0. Or we can use the fact that log of analytic function is subharmonic and try to deduce it from there. There is a nice argument how Kerr-Lehmann inequality can show you this fact. You just have to choose your function phi in a very wise way, using the harmonic measure of this part of the boundary. And in higher dimension, it's an open problem, and it's open problem because I set C infinity here. There are counterexamples of Bourgain and then Wolfenbourgain saying that if you don't want this regularity, but you want just some regularity like C1 alpha up to the boundary, it's not true anymore. But what is the right regularity, and if it's question, and if it's true with this C infinity C, as far as I know, no one knows. But it shows you that we don't have Kerr-Lehmann inequalities in high dimensions that are so powerful in dimension 2. There is no machinery there, but there are still some. And version of this problem, what can you do if what you know is that if the function is 0 on an open part of the boundary and the gradient is 0 on a subset of the positive measure. For the ball, it's an old result. And then you can ask what is the regularity of this domain here that you can do. And part of the story that I told you yesterday about monotonicity of the frequency function on the boundary, it was part of the solution to this problem, first with omega, that is, instead of unit ball, you have a omega. U is open set on the boundary, right? First, when it's a convex domain, when you can have monotonicity, then C1 unique domain, and by Shari, when it's Lipschitz domain with small Lipschitz constant, then you can show this uniqueness result. But part of our trying to get the estimates as quantitative as possible is to see if we can go close to this problem and can have some uniqueness for the probably. Yeah, I hope it was a hint that it's time for break, but it's not yet. A couple of more minutes. Good. So yes, we I think it was some classified information that I was trying to tell, but I should not tell you. So, let us stop here now, and after the break, we will do this exercise using the Coleman inequality and show how to bound the number of critical points over almost monolithic function.